Welcome to the deep dive. Today, we're tackling something truly cutting edge, the quantum internet. We're going deep into the tech, the physics, and yeah, the global race to build these quantum networks. We've got a solid stack of sources here covering, well, everything from the nitty-gritty science of entanglement to actual real-world tests over commercial fiber.
That's right. And our mission here, I think, is pretty crucial. We need to cut through some of the hype, and really understand the engineering reality of quantum communication, or QCOM. We're digging into these reports to figure out the actual protocols, the hardware breakthroughs we still need, and honestly, the massive technical challenges. Basically, the big question is, how do we go from these really delicate lab experiments to a network that's scalable, integrated, and maybe even spans continents?
Exactly. And to help you make sense of this huge challenge, we're slicing it into three parts. First, the bedrock, quantum security. Why are we even doing this? Second, the core technical hurdle, scaling this fragile stuff over real distances. And third, what can we do with it? The applications and, yeah, the global race shaping it all. So let's start right there with the motivation. Security. Why do we fundamentally need quantum networks? Isn't the regular internet, already pretty locked down with crypto?
Well, the main driver, the big one, is the threat from large-scale quantum computers, fault-tolerant ones. These machines, once they're built, will likely be able to shatter the math underlying our current public key crypto. Think RSA, certain types of AES, the security we rely on today based on problems classical computers find impossible. That could just evaporate.
Okay, wow, so that really forces our hand. We need solutions that quantum computers can't break. And the sources seem to lay out three paths: classical, quantum, and this thing called post-quantum.
Exactly.
Yeah.
So classical crypto, that's what we use now. Security relies on hard math problems. Then there's quantum cryptography, mostly quantum key distribution, QKD. This sidesteps the math altogether. Its security comes from physics, the laws of quantum mechanics. Try to eavesdrop on a quantum key exchange, the quantum state gets disturbed, and boom, everyone knows. It's fundamentally secure against any computer now or future.
Fundamentally secure sounds pretty good. So why isn't QKD everywhere already? What's the catch?
The catch is the hardware and the cost. QKD needs specialized gear, dedicated photon emitters, receivers, often its own dedicated fiber optic lines because the signals are so incredibly faint and fragile. The sources are clear. Building out enterprise or national QKD infrastructure, you're talking multi-million-dollar investments.
Okay, yeah, that's a serious barrier. Which brings us to option 3, post-quantum cryptography, PQC.
Right. PQC is kind of the pragmatic middle ground. It's algorithms, new math problems, basically, designed to run on the computers we already have. But crucially, they're designed to be resistant to attacks from future quantum computers. It's more like a software upgrade, not ripping out and replacing networks, so it's potentially much cheaper, faster to roll out. The caveat is its security still relies on mathematical assumptions. We believe these new problems are hard for quantum computers, but we can't be 100% sure like we are with QKD's physics-based security.
Got it. So it's a big strategic choice, absolute physical security with QKD, but it costs a fortune and needs new infrastructure. Or this PQC software approach, which is faster, cheaper, runs on current systems, but relies on, well, hoping the math holds up long term. You've nailed the trade-off. That's exactly the dynamic we're seeing play out.
Okay, let's unpack the next big challenge then. Moving from security strategy to the raw physics of sending these signals. QKD infrastructure cost is one thing, but even with the money, there's this fundamental problem. Quantum information is just ridiculously fragile. How on earth do engineers plan to get these signals across a city, let alone a country, without them just dissolving?
This is the mountain to climb for QCOM. It's really twofold. The fragility you mentioned, which we call decoherence, and just plain signal loss. As a quantum bit, a QUIB, travels down a fiber, its state, its fidelity, it decays exponentially. The further it goes, the worse it gets. The research highlights these high decoherence coefficients.
Decoherence coefficients.
Yeah.
Sounds technical. What does that mean in simple terms for the signal?
It just means the quantum state falls apart really, really quickly.
Yeah.
So if you try to link multiple points in a network, node after node, that overall connection quality, the end-to-end entanglement distribution rate, it just plummets. You can't maintain a useful quantum link over the kinds of distances we take for granted with classical data.
And critically, you can't just amplify it like a normal signal, right? Because measuring it to boost it, that destroys the quantum state itself.
Precisely. No amplifiers. That's why the absolute centerpiece, the linchpin for long-distance quantum communication, is the concept of the quantum repeater. This is totally essential. It's designed to relay quantum information, specifically entanglement, over long distances without destroying it in the process.
Okay, the quantum repeater. Explain the magic here. Entanglement swapping, how does that work?
It sounds, well, quantum.
Hey, yeah, it does. But think of it like creating a chain. Imagine Alice wants to share an entangled link with Bob, but they're way too far apart. We put a repeater station somewhere in the middle. Step one. The repeater creates entanglement with Alice, and it creates a separate entangled pair with Bob, so it holds two entangled qubits.
So the repeater's got one qubit linked to Alice, one linked to Bob, sitting there in the middle. Exactly. Now, here's the clever bit. The repeater performs a special type of measurement, a Bell state measurement, involving both of its qubits simultaneously. This measurement effectively fuses the two shorter entangled links together. It makes Alice's distant qubit entangled with Bob's distant qubit, even though they never directly interacted. That's a swing.
Oh. Okay, so it takes two short, potentially weak links and makes one long one between the actual ends, Alice and Bob.
That's the core idea, yes.
Yeah.
But there's a crucial second part. After the repeater does its quantum measurement, it has to send the result of that measurement, which is just classical information, ones and zeros, over a normal channel to one end, let's say Bob. Bob then uses that classical info to make a small correction, a tweak, on his qubit. And that action finalizes the long-distance entanglement. So you need both the quantum link and a fast classical link working together.
Ah, that dual channel thing is key. Okay, now, current quantum network attempts, the sources say, often use static connections, like booking a dedicated line, which sounds inefficient if you want lots of users. This brings us to scaling. How are engineers planning to manage all this complexity, the quantum and classical channels, and scale it up for many users and applications?
Yeah, that static circuit switch approach doesn't scale well. So we're seeing a big shift in thinking, much like the evolution of the classical internet itself. Researchers are really focusing now on dynamic switching, things like packet switching or burst switching. These are seen as way more practical for handling many users and sharing the network resources flexibly.
Dynamic switching makes sense for users, sure, but why burst switching specifically? Does that help with the physics?
It does, particularly with something called crosstalk. That's the interference you get when you try to run delicate quantum signals in the same fiber as powerful classical data signals. By sending data in controlled bursts, engineers can manage the timing better, basically coordinating traffic to minimize the chance that the bright classical pulses will mess up the faint quantum ones.
Okay, so that suggests the path forward isn't waiting for some purely quantum internet. It's going to be hybrid, mixing quantum and classical from the start.
Absolutely. That's the intermediate future. You'll have these local subnetworks using dynamic switching for users, and then these subnetworks will be connected over longer distances using those quantum repeater chains, those teleportation channels we talked about. It tackles both user scaling and distance scaling.
And we literally just saw a huge proof point for this hybrid idea using existing cables.
Yes. That Philadelphia Q-chip demonstration in 2025 was, well, frankly, pretty monumental. Penn engineers sent quantum signals over commercial Verizon fiber, regular internet cables, and they used the standard internet protocol, IP. I mean, think about that. Quantum data speaking the same basic language as the classical internet on the same wires.
And the key was this Q-chip.
Yeah.
Built with normal silicon methods.
Exactly right. A silicon-based chip that manages the handshake between the fragile quantum signals and the normal data traffic. Yet fidelity's over 97% across the kilometer link.
Yeah.
And because it's silicon, using standard manufacturing, well, that suggests it could be mass-produced relatively cheaply. That plugs directly into existing infrastructure. That's a potential game changer for actually deploying this stuff affordably. So, okay, we've talked security and getting the signals there. Let's look beyond just sending keys. QKD networks, stage one, they're already popping up, South Korea, Switzerland. But the real revolutionary stuff comes later, stage three. Quantum memory networks. Networks that can actually hold and process quantum information for complex apps.
Right. So when we talk about those truly transformative quantum network applications, what are the big ones highlighted in the sources?
Distributed quantum computing, DQC. That's probably the most significant near-term one. See, building one single, huge, perfect quantum computer is incredibly hard. The more qubits you add, the more noise and errors creep in. DQC tackles this differently.
How does networking change the game for quantum advantage? Is it suddenly less about who has the biggest single chip?
That's the critical shift in perspective, exactly. Instead of one giant monolithic processor, DQC envisions networking together multiple smaller, high-quality quantum processors. They share entanglement across the network, and this allows them to pool their resources, collectively performing computations far beyond what any single one could do alone. So yes, the advantage might shift from sheer size to efficient, high-fidelity connectivity.
That totally reframes the whole quantum race. Fascinating. Okay, what's application number 2?
Quantum time synchronization, QTS. This uses entanglement spread across a network of, say, atomic clocks to synchronize them with unprecedented precision. We're talking timing accuracy that gets close to the fundamental limits set by quantum mechanics itself.
Near perfect timing. What's the practical impact of that?
Imagine creating a single global timescale, a world clock, that's incredibly stable and accurate. Think about GPS and satellite navigation, high-frequency financial trading, synchronizing telescopes for deep space imaging. Any application relying on exquisitely precise timing over large distances could see dramatic improvements.
Wow, okay. That sounds like fundamental infrastructure for the future. And the third big one?
Blind quantum computing, or BQC. This is about security and privacy in the era of quantum cloud computing. BQC is basically a set of protocols that lets you run a computation on someone else's quantum computer without them ever knowing what your input data was, what the answer is, or even precisely what calculation you asked them to perform.
So it's like delegating the hard math problem without revealing your secret formula.
That's a great analogy. It's crucial for protecting sensitive data or proprietary algorithms when you're using networked quantum resources.
Okay, switching gears to the global picture. This is obviously a high-stakes race. Where are different countries focusing their efforts based on the research output?
Well, you can definitely see some strategic specialization emerging from the academic publications. China, for example, is the clear volume leader in quantum communications research. They've put a massive effort into overcoming distance limitations, especially with their pioneering work in satellite-based quantum communication, extending the reach.
And how does the U.S. strategy compare?
The U.S. tends to lead in quantum computing research output, especially if you look at metrics related to impact and quality, like citations. So you see this sort of division. China pushing hard on the long-haul communication network infrastructure, the U.S. pushing hard on the core computing power. Europe and others are also major players, often excelling in specific components or quantum sensing.
With all these different groups developing different pieces chips from one place, repeaters from another standardization seems like it would be absolutely vital, like right now.
Oh, it's completely non-negotiable if you want a real market to develop. Standardization, led by groups like ETSI, ITUT, ISO. That's what ensures interoperability. It means a Q chip from company A can actually talk to a repeater from company B. Without standards, you get silos, vendor lock-in, and the whole ecosystem stalls. They actually started thinking about this fairly early for QCOM back in 2008 with that ETSI group focused on QKD.
Is there a particular complexity they need to tackle for quantum standardization?
Yeah, the sources talk about this matrix structure, meaning many of the essential underlying components, things like control software, specialized lasers, quantum memory modules, aren't just used for communication. They're also fundamental to quantum computing and quantum sensing. So standards need to work across these different pillars. If the basic building blocks aren't compatible, you end up with 3 disconnected quantum worlds, which severely limits the potential. So, wrapping up the core challenges, the sources really emphasize that while we're making strides, especially with hybrid classical quantum systems, the big roadblocks remain those key technological enablers. We're still waiting for truly practical, efficient, scalable quantum repeaters. And alongside that, significant improvements in quantum transduction are needed.
Right. Transduction, that's the crucial bit for converting the quantum signal from a photon flying down a fiber, the flying qubit, into something stored in a node, a memory qubit, and back again, right? Without that, the network can't really process or hold information effectively.
Exactly. It's the interface between communication and computation or storage in the quantum realm.
Okay, so if we pull this all together for you, the listener, this shift towards networking quantum devices, it potentially changes the whole game. Maybe the future isn't about who builds the single biggest, most complex quantum behemoth. Maybe it's about who can master building the most efficient, reliable network of smaller, high-fidelity machines working together through distributed quantum computing. Think about that implication. If connectivity becomes the defining factor for quantum power, how does that shift our understanding of who's really leading the race for quantum advantage? It's a fascinating thought to leave you with.